Okay, welcome everybody. So as promised today, we will be talking about MVCC versus Git, and the presentation will be given by Sue Yilmaz. Sue actually was in this class 2 years ago. So she did her bachelor's degree in Chicago, University of Chicago from 2014 to 18. And then she joined this lecture. And then at some point, I was looking for HEVs for the master application system we are developing. And Sue joined and is still working on that system. And then we started working also on research topics here and there. And eventually, she entered our grad school. I'm not sure whether you know about that. We have this graduate school that allows you to skip the master's degree. So there's a fast track where you can enter directly from your bachelor's degree into the PhD without doing a master thesis. And yeah, that's what she's doing. And she is doing some very interesting, great research. And one is about this stuff. And why is this interesting? Because it revisits decisions taken in the past. So many of the things we did in this lecture already were along those lines. If you remember, if I question APIs of database systems, APIs of component XYZ, and that's along the same lines, but on a more system level. So if Git does versioning and MVCC does versioning, why is it two different systems? Similar story as of, okay, why do we have file systems and database management systems? And there are many lessons you will see you can learn from this talk. It not only has ramifications for Git, but also for MVCC and what MVCC is doing and what databases are doing, but you will see. And the talk you will be seeing is actually her first paper being accepted at CIDR. CIDR is going to happen next year. That's our biggest conference with regards to systems. So in databases, there are like 3 conferences that are important. This is one of those. And this is more systems oriented. This is more like, okay, here's a fancy idea, let's play with that. You don't have to have full-blown experimental results and stuff like that. So I really like that conference. And the presentation she will be giving next week is 15 minutes for all of what you're showing today, what you're seeing today. So this is a way longer and slower version of that to be able to digest this stuff. If you have any questions, just ask. We can do that interactive, scribble things on the blackboard. And without further ado, the stage is yours.
Hello, everyone. Well, thank you, Jens, for the introduction. Jens has already a bit started on our motivation, but to explain it a bit in more detail. So we are developing this system called generic version control, or generic VC for short, which can basically act both as an MVCC database and also a version control system. And why we wanted to build such a system? We start with the following observation. Assume that you have a database of city names. And here, first of all, a remark. I guess in the lecture you have looked at things from more of a non-relational perspective. There was the implementation of MVCC, which was built upon this key value store. Here I will look at things from a more traditional relational perspective. So you will see a lot of tables in old style. I hope this can also help you draw some parallels and understand both systems better. So, okay, starting with our example, we have these city names, and we have a user, Alice, who wants to work on this table. What she does is that she starts a transaction, selects some of the city names that she wants to read and work on. So this makes some entries in Alice's private workspace. Then let's assume she wants to fix a typo. So she does an update, runs an update query, which creates this new version of our tuple, which I think you call it work in progress version. Then when Alice wants to commit her changes, she runs the commit command, and this is what we get in a relational world. We get the second version of the same tuple. We only have, the difference is that we have some meta columns. The first one being this row ID, so that you can distinguish between different versions of the same tuple. And also you have these VB and VE, meaning validity begin and end timestamps. So you know that when does the validity of a version ends and when does the validity of the next version start. So when Alice adds this new version, we obviously now the validity of the old and version with the typo ends, and now we start the new version. Well, now this process is pretty similar in Git. So let's assume that we are doing the same thing with Git. Maybe you would not want to record your city names in Git files, but just to draw the parallel, assume that you have different files, and in every file you have this one city name, and now Alice wants to make the change again. Now instead of starting a new transaction, she starts a new feature branch, and she opens the files she wants to check out and update. Then she sees the typo again and updates this by running git add and git commit commands. And this also creates a new version similar to MVCC. And this version, when Alice wants to commit this and make this version visible to everyone, she switches back to main branch and merges her changes to the main branch. So the merge feature here is similar to a transaction committing. And also similar to MVCC, now we have this hash column, which is similar to this is in Git, this is not like a column, but just for the representation purposes, we have this hash values that can act as these validity timestamps, because then, based on these hash values, you can follow different commit objects, which I will discuss soon, and you can find which version you want to work on. So based on this similarity, we asked the following research questions. First, we wanted to explore more. What are all the similarities and differences between an MVCC database and Git in terms of their versioning, storage, and transaction processing requirements? To answer this question, we first investigated and formed a logical comparison between the two systems. We are going to first compare the transaction processing mechanism and asset properties in MVCC and their Git equivalents. We will look into conflict detection policies in both systems and how commit validation in MVCC works versus, again, their Git equivalent. And also, we are going to briefly look into physical comparison, meaning how data is organized, accessed, and manipulated in both systems. Then we asked the second research question, which was, if these systems are really similar, why do we have two different systems to maintain? Can we unify these systems and come up with a single system? Well, we present three main differences between two systems that we must address, and we propose 3 solutions to create our system called generic VC. And in the way, we also realize that, there are some gains for the database world, meaning the databases and MVCC-only system can also gain some insights from thinking about this comparison between MVCC and Git. So before I start the comparison, I want to just briefly describe what a version means in each system. In MVCC, a version is a physical representation of the same tuple in different states. So here, both these rows, tuples, are versions of the same logical tuple, which is actually this part, right? It's actually just the ID and name, our table. But then we have these meta columns that we need to, in order to present these logical tuples physically. And also, we have additionally this previous version column, which we can use to form version chains. So we can access prior versions of the same tuple just using the latest version. So this is somewhat similar in Git. So we have versions are here the blob objects. If you know, these are basically what keeps these blob files keep the entire content of each of your files in a Git repository. So this is, for example, your previously I have shown, I think it was some d.txt file. This is the same file, just represents the newer version. Well, how do you follow the version chains here? You also have, in addition to blob objects in Git, you have tree objects, which represents directories. And then you also have these commit objects, which are the objects that are created when you run git commit, basically. And using these objects, you can follow the, so basically your newer commit object points to the parent ones that have been that have been changed. So this here, the upper commit is your older commit object, and once you make a change, the newer commit object only keeps the files that have been updated since the prior commit. So basically, the commit object, you might have also heard of it, it acts as a snapshot of the entire repository, which means that following one commit object and its parents, you can basically generate the entire repository. So again, here the MVCC has tuple versions, while Git has these blob versions, and these commit objects as helper to follow our chains. So starting with our comparison, I think you have briefly seen this in the prior example, that transactions in MVCC look similar to branches in Git. So in MVCC, we have our global data. Let's say this is just one table, and we start a transaction. We make some inserts and updates. These create new versions of the tuples that we have. And when we want to commit, we commit these new versions to back to our global data. And you can do this with multiple transactions concurrently as well. But in Git, well, first of all, the similarity is that you have branches in Git, and what you can do is, in this, we have this main branch and one commit object here. And by the way, I will, from this point on, I won't be showing the blob and tree objects just to not to clutter the entire slide. But obviously, this commit object has some blobs that have been changed in this commit. So we have our main branch, and if we want to start a new transaction in MVCC, in Git, we would start a new feature branch. And maybe we, again, insert and update some files and then commit them, so which would create this commit and point to whichever snapshot it has started from. So far, this is quite similar. What is slightly different now, it slightly gets different, is that we can also start a feature branch from a feature branch. And we can make this multiple times. We can also commit to a feature branch, not necessarily to the main branch. And we can make even get crazier and commit to a main branch from a nested feature branch. Well, this is the main difference between transactions and branches, which is that in Git, we can select exactly which snapshot of the repository we want to work on. If feature branch 2 wants to work on specifically this snapshot, it means that I can see all the changes that has been made up until this point in main branch. I can also see the changes made up until this point in feature branch 1, and then I make my changes on these changes that I see. In MVCC, we do not have this flexibility. For example, when T2 starts, assuming we were working in isolation level read committed and above, T2 will not see any changes made by T1 or other concurrent transactions. Well, in MVCC, we could work in read uncommitted level, but this would not provide us the flexibility that Git has, because then we would see everyone's uncommitted changes, not just a selected set of transactions or a selected transaction. So this is one change that we need to address in our new unified system if you want to serve both an MVCC-like workload and a Git-like workload. So next, I will move on to asset properties. First, atomicity. As you know, atomicity is the all or nothing behavior. If assume that you have this two versions of the tuple. Now we want to, so this is, maybe I can briefly explain what T2 means here. So this T2 is basically, we have this T2 transaction, and it's about to commit its changes, but it has not committed yet. So basically, this version here, with T2 as the validity begin timestamp, means the work in progress version in the lecture system. And to be able to, so in the lecture, you had one work in progress version, and if another transaction wanted to write to this tuple again, it would see that, okay, the work in progress version, there is a work in progress version, so I cannot start writing. How we do it in a relational world is that we put this T2 timestamp in the validity and interval of the committed version, so that no other tuple can try to write to this. And then for this next version is the work in progress version itself. No tuple can write to this, and also no other transaction can write to this, and no other transaction can also read this work in progress version. These are what it means. So now if this transaction is going to abort, we obviously just delete this. I mean, we mark this tuple for deletion, and it's going to be garbage collected later. If you want to commit this, instead, we change the transaction timestamps to actual timestamps, so that now this means that both of these versions are committed, and the prior version, this is now the old version, only valid until timestamp 7, and this is our new version, new transaction starting can work on this version. So this is like we have this all or nothing behavior in MVCC. We also have all or nothing behavior in Git, which is that assume that we have one feature branch here that started from main, and this is our branch pointer. Some of you may already know branches in Git are just pointers to the last commit object. So now if you want to merge this feature branch to the main branch, if there is any problem with this merge, your branch pointer is still pointing to this commit object C1. So any of the changes that are made by this feature branch are not yet visible to anyone who wants to start a new branch from the main branch. So this means that none of the changes until you can successfully commit, you can successfully merge to main branch will be seen by any other branches. And if you obviously can successfully commit, you successfully merge. Sometimes I use commit and merge interchangeably since they're the equivalents. The last step is moving this branch pointer to the last commit object. So now everyone can see changes merged to this main branch. This is the all behavior of atomicity, that all your changes will be visible at once. So atomicity is pretty similar in both systems. What about consistency? Well, in MVCC, let's assume that we have the same cities table, and now we have this constraint that says our population cannot be less than 0. Now, if we want to make a change to our system such that we want to set population to a negative value, we won't be able to do that. The transaction will be immediately aborted because we have our check constraint. Therefore, our consistency is kept stable. And if in Git, we also have a similar mechanism, which is called Git hooks. You can write, for example, a pre-commit hook, meaning that right before you commit, this executable is going to run and check that, this executable is going to run successfully. So what are we doing here is that this is not exactly the same example, but just so that it makes more sense in Git, you can do something like this. You can get all the files that are listed for your next commit, and you can run, for example, a formatter. Maybe you want to make sure that all your files are formatted properly. And if it's not, this is just going to, your executable is going to fail, and you won't be able to commit. So what's going to happen is that you can add your, you can do git add and add your blob object to your git objects repository. But when you want to run git commit, which is the command that creates 3N commit objects, this will not be successful. So again, we have some similar mechanisms to keep the consistency in the system. Moving on to durability, I will talk isolation later. So in durability, as I think you have already seen this write ahead log logic, We write our changes to main memory first, and then we represent those changes in the repository. And then once we flush to hard disk, we also make our changes in the database permanent. So this idea is that even when there is a failure and your transaction can be rerun and committed, it unfortunately does not exist on Git. What does exist is that Git has some sort of consistency check, not check, but at least consistency guarantee when something fails. And it is the following. So let's assume that you have a feature branch and you just in the phase of merging to the main branch. So your commit object in the main branch is created, but your main branch pointer is still not yet moved. This is the last step. So unless your main branch pointer can move to here, any of the failures, any of the problems that happens during merge will not be reflected to the other branches. So Git can only provide this consistency, and it cannot, but if an error happened at this point in time, Git will not be able to rerun the merge and successfully move the branch pointer to this one. It's up to developer to fix the problems with the merge and try the merge again.
Maybe that's interesting also in the light of what we discussed in the previous. So that's actually pointing to the version that is considered the current version. So the pointer indicates you first do the changes.
Right.
It's like in our durability lecture, we flush, now we create the log entries, and only on commit we flush. And this is kind of similar. Flushing is similar. I mean, assuming that the pointer is also somehow materialized on disk or the log or something, the pointer is a point of truth here, saying, okay, that is my branch, right?
Yes, right.
Okay. Mm.
So moving on to isolation, in MVCC we have 5 isolation levels, starting with read uncommitted. We have how this level is represented in database as follows. In these validity intervals, now instead of, let's assume that a transaction is working on this tuple again, instead of putting transactions timestamp in validity end and validity begin intervals here, timestamps here, we just put null values, which means that any other transaction can also start working on this tuple, and also any other transaction can see uncommitted versions. If we move to read committed isolation level, obviously we would lock these both tuples so that now no other transaction can see the uncommitted versions. To support repeatable read, in addition to this, we would also need to keep a read set inside of our transaction so that next time we read the same tuple with ID 4, we are going to be reading the same version of this tuple. Now, next to support snapshot isolation level, in addition, we need to keep a start timestamp for the transaction to make sure that this transaction is not going to read anything that has been committed after this timestamp. So anything after I started, I don't care. I just care about the snapshot of the database until this point in time where I started. And next, to support serializable isolation level, we obviously need a commit validation phase, which you have already discussed in class. We had 2 options for this, checksumming and write sets. So I won't go into much detail, but in addition to snapshot isolation, we have to have this validation phase to ensure serializable isolation level. Well, in Git only supports 2 of these levels. The first one being read uncommitted. Assume that, again, you have a main branch and a feature branch. This feature branch has started from this prior commit of main, and then some other changes happen to main. Now we start a new feature branch from the latest version of main, make some changes, commit them here, and now what we can do is we can merge some changes from feature branch 1. This is, in MVCC world, a read uncommitted isolation level because this feature branch 1 changes have not been merged to main yet. So they are right now uncommitted versions, and I'm still reading them from another branch.
So in theory, we could, if we extended Git to forbid feature branches to read from other feature branches, then we would disallow that, right? Then it would be more similar to database.
Yes, right.
The problem starts because you allow that. I mean, it's okay. It's also a feature that makes sense in Git a lot, but yeah, okay.
Or maybe we could allow that in MVCC.
Yeah, sure. It's always the other way around.
Yeah. And the next isolation level supported in Git is the snapshot isolation. This is actually the default level, unless you want to deliberately merge things from other feature branches. And let's assume that, again, feature branch started from main, and then some other feature branch has merged changes to main. Now, this change will not be visible to feature branch 1. It will still care about all the things that happened up until this point where it started, and also it will obviously see its own changes. And when it comes to serializable, Git unfortunately does not support this. Because during commit validation phase, what Git does is that, in MVCC, as you might remember, in validation phase, we are checking for read-write conflicts because we are already preventing write-write conflicts because we have allow only one work in progress version, so no other transaction can write to what I'm writing anyways. So in the validation, all I have to do is look for read-write conflicts, and then you are done. You can support serializable. But Git does not have this first check before the commit validation phase. It allows multiple work in progress versions. So what Git does in its own commit validation phase, which is namely the merge, is that it now checks for write-write conflicts, and it does not check for read-write conflicts. That's why it cannot support serializable. And while doing this, Git also does some semantic conflict detection, which means that, in the class you have seen that we check for the transactions that started after a transaction, transactions that have committed after a transaction has started, and you take a union of their write sets, because these are all the versions that I need to check against to make sure that my predicates do not conflict with these versions. Well, Git also takes a union, but it's not an actual union. For example, let's say there are two feature branches that have been merged and they delete the same file. In this case, Git would, created the exact same file. In this case, Git would take just one file, get their merge, and just one file, not two different files. And I will go a bit more into detail in this, but Git is doing some semantic checks here as well during conflict detection. So to talk about this commit validation phase, finally, again, to run an example, let's assume that in MVCC we have two transactions, and transaction 1 starts and creates a work in progress version here. Now, if transaction 2 wants to write to the same tuple, obviously there's already a work in progress version, so it aborts. And even if it wants to read, when transaction 1 commits, if this transaction 2 has made some updates here, its commit is still going to be not going to be successful. So in Git, this is a bit different. Let's say we have two feature branches, and they both try to write some versions of this file. Well, if feature branch 1 merges, it can obviously create its version in the main branch. But now, if feature branch 2 wants to merge, well, this will also be successful because these changes are happening in different lines in the file, and Git can do here what's called a three-way merge. So what Git does is, even if there's a conflict, I do not blindly abort like MVCC does. I try to reconcile those conflicts. I try to find the middle ground between the two changes and merge them as one version. So it creates this third version, which actually did not exist in neither of the feature branches. So this is also one difference that we are going to address. So moving on to physical comparison, in MVCC, so far we talked about all the examples we have seen are from this storage type called append-only storage, which means that all the versions of your tuples exist in the same table, and your version chains are through, you can follow a version chain through the pointers in the meta tables. There is also another storage type called delta storage. This is actually a newer type of storage that some newer implementations of MVCC use. Here, you only keep one version of a tuple in your main table, and namely the latest version of your tuple. And if you want to keep the other versions, the prior versions, what you do is you keep these versions in your transactions undo logs. So this is, for example, in, let's say, transaction 2 has has made this change and fixed the typo. This is the committed version by transaction 2, and this is the older version in transaction 2's undo log. So if you want to undo the changes, you have to follow these pointers and go to the undo logs. Well, what's the advantage of this delta storage? Obviously, you can, your scan queries will be performance-wise better, because now you don't have to filter out these older versions. You can just scan the entire table once, and you can give this to the user.
Maybe just as a clarification, as we talked about logging last time, so if I understand this method correctly, this is an undo log per transaction, not a log that's written, a log record written to the log. But
right.
Each transaction has to track the information that is required to undo its changes in the case it is aborted.
Right.
Okay.
Right. Yes.
Again, a name clash here. It's a bit confusing, but.
Yeah. So we have similar formats or storage types in Git. Similar to append-only storage, the first type we have seen, we have this loose format in Git. This is the default format. So what happens here is this. Let's say you have 2 files, you committed them first, and then after this, you have made some changes to your first file, file1.txt. Maybe you have only changed 5 bytes in this file. You have added 5 bytes, and then you committed this as well. Now, if you go to your Git objects directory, you will see that this second file, the second version of the file1.txt, is also around 22 kilobytes. So this means that Git, this loose format keeps the entire file for every version, even if there is like 5 bytes of change. This is, you could say this is a lot of storage overhead, but since Git repositories do not have like millions of files, this is fine for Git. But still, Git has this next format called packed format, which you can create actually by running git's garbage collection command. And this takes your entire files here and then creates 2 files called pack.idx and pack.pack. This pack file, the file with pack extension, keeps the entire content of your repositories. So from all the content from all the files from all the versions. And how do you read these files? You go to this index file, and you would see that now your latest version of the file is kept in its entirety here. So you will see this is the file1's second version. And if you want to create the prior versions, similar to delta storage in MVCC, you have to find the prior version and check the pack file to find its reverse delta. So which means that on this file, you apply this reverse delta, and you can find the older version. This is just like the delta storage in MVCC.
So again, it's kind of an undo log for the file, right?
Right, yes. Yeah. Right. So, okay, to summarize our comparison, we have actually found 3 main differences between MVCC and Git, and we need to address these. First, when it comes to when we made the comparison between transactions and branches, there was this flexibility in Git to select which snapshot we want to work on. Versus in MVCC, we could only work on the global table. The second one being when it comes to conflict detection, in MVCC, we did read-write and write-write checks on the tuple level. In Git, we only did the write-write checks, and we had this multiple work in progress versions initially, and only did write-write checks, and we did some semantic conflict detection as well. Next, when it comes to conflict reconciliation, we have seen that Git can reconcile conflicting versions. It does not abort every time it sees conflicts, whereas MVCC offers no such reconciliation, and it aborts transaction as soon as it sees a conflict. So to address these three changes, differences, we propose the following. First, we want to reintroduce this old idea called nested transactions into database world so that we can provide the flexibility of Git-style branching. Next, we propose to have a configurable conflict detection policy so that we can define what a conflict means based on our application, whether it's an MVCC-only application, whether it's a Git-style application, or whether it's some hybrid workload that we want to define a conflict just for that workload. And third, we also want to have a configurable conflict reconciliation policy, both to support Git-style application, so Git-style merge, and also we are going to see that this is going to help us reduce abort rates even in MVCC workloads if we implement this. So starting with nested transactions, this is how the old idea works. Given that you have, again, your global data, you begin a transaction, T1. Now what you can do is you can start a transaction, a sub-transaction from T1 called T2, and you can do this multiple times. And you can also make your changes concurrently in all these transactions and make it as much nested as you want. So this would help us create a Git-style branching now, because T2 can, similar to a nested feature branch, T2 can see all the changes committed to global data and also the changes committed to T1, of course, until T2 has started. So, so far, they are very similar with this old idea, but there is a catch in this old idea of nested transactions, which is that if you want to commit T1 right now, you actually cannot do this. You have to make sure all of the children of T1 has been resolved, which means that they have to be either committed or they have to be aborted. And also the second thing here is that let's assume you want to commit T2 to your global data. You also cannot do that until T2's parent has been committed to global data. So these are two restrictions that we need to remove from nested transactions in order to support Git-style branching. And if we do that, now we can really have this branching feature in our nested transactions because, well, we are doing things very similar. We can start nested transactions, and once we want to, let's say we want to commit T1 without their children being resolved, we commit this, but what we do is we keep this private workspace of T1 around until all its children have been resolved. So that way, T2, T3, we don't care about them. They just keep their parents' workspace, and we can commit whichever transaction we want without caring about their children's or parents or grandparents. So this way, we can really, in a unified system, support both an MVCC-style application by just simply not using the nested versions, and also Git-style branching. Moving to configurable conflict detection. So assume we have a similar example again. We have transaction 1, and we started 2 sub-transactions from transaction 1. Now, what we want to do is, in MVCC, obviously, to detect conflicts, what we were doing is we make sure the write sets do not conflict, even before commit validation phase. And then we also need to make sure the predicates of the transaction committing do not conflict with the write sets. Well, in Git, we do the following. We compare the write sets of the committing transaction with the write sets of the transactions that have already been committed. But what we also do is, for example, if this transaction T3 created some version that is exactly the same version in the parent, we don't have to count this as a conflict. This is what I mean by introducing semantics to this conflict detection, because this is only a case you would do in Git. In MVCC, like what would happen if you try to do this? Let's assume you have a tuple and you have a population column in this tuple. And let's assume two different transactions try to reduce this population column by 10. Well, we would have two exactly same new versions, but obviously accepting the same version here would cause us so this would result in a lost update problem, it's called. And what you should do is you should serialize them and instead subtract 20 from the total population. But in Git world, you just end up subtracting 10 from the top population. So this is why I'm saying this is only a semantic detection policy you would run for Git and not for MVCC. But similarly, if you deleted the same version, or if you inserted a version in parent and then later dirty read the version and updated, you can also filter out conflicts like these. So this is why we are saying that our conflict detection should be configurable. So to show, maybe I will draw a small example to explain this different conflict detection policies on the board. So let's assume that we have, I don't know, we have like a shop and we have some stocks in the shop. So we have some items and then we have the stock count and we have our item A and it's like there are only 5 of this. Is it visible?
Yeah.
Only 5 of this. So now, and we have 2 transactions, T1 and T2. Now, transaction 1 tries to do A stock, it tries to decrease it by 1. And transaction 2 tries to do the same. So here, I mean, if they're concurrent transactions, we have to serialize them, right? They have to be one after another, and the resulting stock, like the resulting stock count has to be 3 at some point. If this is not the case, if they're concurrent, in MVCC, we detect a conflict and abort one of them and maybe restart the transaction, and then finally we reach this 3 count. Well, in Git, this is actually happens as following. We have feature branch 1 and feature branch 2, and they both do try to decrease the stock count, but here the resulting values, let's say this branches merges first and this merges the second. Well, here we have the value 4, and at the end of this merge, well, we are also going to see the value 4. So Git is going to see, okay, this is not a conflict for me. And then while MVCC says the result after both of these transactions is 3, Git is going to say the result is 4. This is what I'm trying to say when Git's doing this semantic detection and not counting this as a conflict. If you try to do this in MVCC world, this is a lost update problem. And this is actually exists in a database called DOT, for example. They are trying to advertise themselves as Git for data, which is they are trying to introduce Git's features to a database. But they, I mean, as of last month, they still had this lost update problem. Even though they were a database, your transactions, concurrent transactions would result in 4. So this is what we want to configure based on what your workload is. Oh, yes?
Can you please explain again why T2 doesn't abort here?
So maybe I didn't write it very clearly. Obviously, in MVCC, this would abort. This would commit. I can write it in more detail. And let's say we restart it, because in some systems, if a transaction aborts because of a serialization failure, it's going to start again. Yeah, -1 equals 1, and then it commits. Yeah. Okay, yeah, this is more this is the right version. Yeah. Yes. So moving from conflict detection to conflict reconciliation, and also give an overall idea about how our commit validation phase will look like. So this is what we want to do in our unified system. In our commit phase, we want to detect conflicts, and then what we want to do is we try to reconcile conflicts, and if our reconciliation results in failure, we abort, else we successfully commit. And what we want to do is introduce two functions called detect conflicts and reconcile conflicts, and these will be now user-defined functions. So if there's a user who wants to work with an MVCC type workload, it's going to write these detect conflicts algorithms and reconcile conflicts based on their own needs. And if there's a user who wants to use a Git-like workload, they are going to write a different type of algorithm according to their needs. And here, reconciliation, for example, in Git, it's possible that user does not define any reconciliation, because in traditional way, there is no reconciliation in MVCC. In Git, it works as the following. Assume that we have a parent version, a version that has already been committed to your parent transaction, or if this parent-child relationships confuses you, the nested transaction idea, you can also think of these as this is the global version, global data version, and this is just one transaction that is trying to commit to global data. Now what Git does is it creates a reconciliation version by merging these two files. And what we need to do here is, in our unified system, what we first did was we detected some conflicts, and we also obviously detected this as well. Well, what we need to do is now reconcile this. Okay, yes, we also reconcile this, but what happened is that after we started our commit validation phase, we created a new version. And this is not good in the sense that we also need to make sure this newly created version has also been run through this detect conflicts algorithm. So what we do is, actually, we don't just detect and reconcile once, but we try to reconcile, and as long as we create new versions, new reconciliation versions, we put them into a loop and keep checking if any newly created version is causing any new conflicts. I will walk through a coding example, and it will make more sense soon. So, but before that, I want to go over this online game store example. So maybe with the example, it can make more sense. So let's say we have an online game store with two tables, an inventory table and a shopping cart table. And we have two users, Bob and Alice, and they are one of them is trying to run one game, the other is trying to buy two games. And now they click on purchase about at the same time. So what we do is we create 3 transactions for each one of the purchases, because this way, even if Alice's one transaction can abort, the others can still go through. And what they try to do is they try to obviously write different versions of the game stock. So now, let's say Alice's second transaction commits and successfully gets out of the way. So we don't care about this. And what we want to do is talk about Bob's transaction and Alice's first transaction. So here, actually, before even running these commit phases, what is going to happen in traditional MVCC is that Bob is going to, right here, Bob is going to lock the tuples. So it's going to lock the actual tuple, and it's going to create its own work in progress version, and it's going to say that stock count is 0. So now, if Alice wants to write this transaction, it's going to actually fail, and Bob's transaction is going to be committed successfully, and the stock count will be reduced to 0. Now we retry Alice's transaction and try to commit, but what happens here is that Alice tries to reduce the stock count to -1 this time, and assuming that we have already a check constraint that says stock count cannot be 0, this transaction is going to be aborted once again, and we have to send a response to our application server. This means that In traditional MVCC, this transaction, Alice's first transaction, aborted 2 times, and we also have to connect to the application server, which takes even more time than just trying to resolve the conflict in the database level. Well, how we are going to do this in our unified system, we are going to, with reconciliation, is the following. We again have the same example, and Bob and Alice try to write their own versions again. Now at this point, similar to Git, we have multiple work-in-progress versions, which means that Alice's transaction is not going to abort at this write operation. So we keep both versions here, and we also keep both versions of the shopping cart. These del means these versions are about to be deleted. They are marked for deletion, basically. So now, if Alice tries to commit again, well, Alice is going to be successful this time, and it's going to reduce the stock count to 0. Now what's remaining is Bob's transaction, and now we are going to try to not only commit Bob, but also if we detect any conflicts, we are trying to reconcile this transaction. And how are we going to do it? We are going to say that, okay, keep this version of Bob's as marked as deletion, and instead of trying to reduce the stock count, put this version into a wish list table. So once we do this during our reconciliation phase, now Bob's transaction is going to be successfully committed because it did not change the stock count at first. Well, what's the difference between this version and the prior version? It actually, as a result, the same thing is happening. In the first version, Bob has tried, it was Alice. Alice's transaction failed. It sent a response to the application server, and application server probably, there would be some logic there saying that, oh, okay, the stock is not enough, so instead I will move this order into a wish list table. But, and the same thing is happening in this example as well. The only difference is that in the prior example, we had 2 transaction aborts plus an extra round trip between application server and the database server. And this is just too much performance overhead. Here, we didn't have to go to application server at all, and we had no aborts. We just did this reconciliation in our commit validation phase. So to go over the code a little bit more, so here is how our commit validation algorithm would look like. Assume that we have a transaction T that we want to commit, and we have a validation strategy here, a user-defined validation strategy. So now we want to commit this transaction T to our parent. Again, you could think of this as the global data as well, assuming a non-nested situation. So here, what we first do is get all the transactions that have been committed to this parent after T has started. So all the transactions that could be in conflict with T. So we get these committed versions as of T's begin, committed after T's begin timestamp. Now what we do is we run our validation strategies, detect conflicts algorithm with T's write set, T's predicate set, and also our parent write set that we just computed. Then what we do is, this is the while loop that I mentioned previously. If there are conflicting versions, now we try to reconcile them. So we start a new reconciliation transaction inside T. So what we have is, maybe I can do it here. So this is our parent transaction, or global data, same. Now we have T here. We are about to commit T, and what we do is, for reconciliation, we create another transaction, T-rec, that we want to, if there are any reconciliation versions, we are going to add it here and try to first commit this to T, and then commit everything in T to parent transaction. That's what we are trying to do. So we create this T-rec transaction, then we run our reconcile function of our validation strategy, and if there are any failed reconciliations, or for any reason our T-rec transactions fails to commit, we say that, okay, we cannot do this reconciliation, we have to abort, and the system has to either restart the transactions or resolve it in the application layer. We can't help you here. If this does not fail, what we do is, okay, now we have some new versions created in T-rect transaction, so we get its write set and its own predicate set, and we run the conflict detection algorithm again. And as long as there are conflicts created by these new versions, we have to start new transactions and so on to make sure until we have no conflicting versions remaining. And if all goes through, we successfully commit the transaction T.
So how do you guarantee termination here of the while loop?
I mean, what we can do is we can put a limit to how many nestings we want to make. But this is actually, I would say this would work best for simpler workloads, but when there's a huge peak of similar transaction, maybe like similar to the stock table, there are some hot tuples, there are products a lot of people want to buy at the same time. This sort of thing, like simpler but very frequent transactions.
But still you want to, I don't know, limit it, or if you have oscillation patterns or something like that, avoid that this runs forever, right?
Sorry.
I mean, you want to avoid that this loop runs forever.
Yes,
right? So,
yes. I mean, like, ideally, as I said, there would be a limit, like maybe have at most 5 nestings.
Okay.
Yeah. So what would our detect conflicts algorithm look like? This is, again, given our transaction T's write set and predicate set against all the write sets from all the transactions that have committed after T started. Now, what we do is, well, previously, in the lecture, you look for only read-write conflicts, but since we had multiple work-in-progress versions in our unified system, we need to check both write-write and read-write conflicts. So this is very simple. What we do is if there are any tuples, any keys that are in both write sets, we just add them to our conflicting versions list so that we need to check them for reconciliation. And read-write set is also similar. What we do is for all the predicates of our transaction T, we make sure that if this predicate can be evaluated, if this predicate returns some versions from this parent write set, or this base version is basically what it means is that, so maybe I can show it here. So we have, well, obviously we initially had one version, let's say version 1. This is our base, or version B. Base version here, and then what happened is that this transaction has started, it created its own version, version T, and after this point, another transaction, T2, has created this new version, I call it version parent because it's the last version in the parent, that's why I call it. And this has been already committed. Now we have to check between against conflicts between this VT and VP, parent version. And what we also need to make sure is if our predicate was evaluating true for either this base version or this parent version. This is what in the lecture you also counted as read-write conflicts. So as long as these are conflicting, we add this to our conflicting versions algorithm so that we can run all these conflicts through reconcile conflicts. So this is an implementation of this reconcile conflicts function for our previous example where we have an inventory table, and this is how it works. So basically now we have 2 conflicting versions, right? Version T and version parent. And what we want to do here is that we again get the base version first. So because this is what we want to do. Let's say there's a stock column here, and in this version, for example, the stock was 5. And in the parent version, the stock was reduced by, let's say, 4, and it was now 1. And in here, let's say the stock was reduced by 2, and it's 3. Now what we want to make sure is if we apply T's version after this parent's version, is the stock count be below 0 or not? So we make this calculation here. We find the final inventory count, and if it's it's less than 0, what we need to do is we need to basically, as I shown in the example, we need to delete our entry, so basically this entry, from the stock count table. And what, yes, here, so we delete our entry, and also, yeah, this is the, sorry, this is the prior version of the slide, so I had a confusion for a second. What we do is we add create a new entry in our wish list table. So in this reconciliation transaction, for wish list table, we insert a new entry, and for our stock table or inventory table, we say this entry that is conflicting version T entry is marked for deletion. This causes conflict and it's not going to run through, so we mark it for deletion. We add it to wish list table, and then so now because our T-rec transaction has two new versions, what we are going to do is we are going to feed them into detect conflicts algorithm again here, and if there are any more conflicts, maybe for some reason these could also cause conflicts with other changes in the parent. So we have to make sure this doesn't happen. And once we feed them here and run through and make sure there are no more conflicts, then we can successfully commit the transaction. Yeah. So finally, I would like to talk about our preliminary experiments. We started building the system, and now obviously one advantage of the system is that we are able to reduce the abort rates, and these are just our initial setup of the experiment. They are not done yet, but I still want to show them to you so that you know what kind of experiment would you run on such a system to prove that it's working, or if there are any performance or other benefits. So in our experimental setup, we have this one table of 1 million items, with each of them having stock counts less than 100. So then we have 100,000 transactions. Think of this like a Black Friday sale on Amazon. Like there are thousands of products, and a lot of people want to buy some of the products. And this is so in traditional databases, you usually have up to 40 threads. So at the same time, at most 40 transactions can run concurrently. So we experiment with 2 different use cases. The first one is similar to TPCC benchmark, where 45% of the transactions are similar to people trying to buy stuff and reduce the stock count. And we also run another use case where we think about like how we can reconcile update transactions versus delete transactions. So here, instead of changing the update percentage, we play with how many of the transactions can be items being deleted from the table, and we initially we just set it to 10% to see how this affects our abort rate. What this means is that basically if there's a delete transaction conflicting with an update transaction, what we do is that we let the delete transaction win. Even though they're concurrent, we say, okay, this update will no longer be available anyways, even if we aborted and retried the delete transaction. So instead of aborting them, we just accept the changes from the delete transaction as the final decision. So here, what we are seeing is that, first of all, we have 3 different commit validation strategies. This is the standard MVCC. There is conflict detection, but no reconciliation. And these are the use cases I just explained. We have reconciliation for 45% of the transactions versus 10% of the transactions in the second use case. And what we also change is that we change the contention levels by using this zip-fin distribution. This means that basically for the database, as your zip factor increases, you are accessing a smaller set of data more. So in the Amazon example, it could be like out of this million products, obviously there should be a few hundred of them that are really popular by people. So everyone wants to access them. This is what it means. And we see that in standard MVCC, we have in our uniform distribution, we have 0.26% of abort rates. And as the contention level increases, it goes up until 3.8%, meaning 3.8% of the transactions have to be aborted and restarted, or even we might have to send a response to our application server. Well, if we reconcile, in the first use case, we see that under high contention scenarios, we can reduce this abort rate by more than 1%, almost 1.5%. And also, even if we only reconcile 10% of the transactions, we can still reduce our abort rates by 0.5%. So as I said, these experiments are work in progress. So the next thing we need to make sure is that our reconciliation strategy do not cause extra overhead, so that our commit validation phase also should not take forever. And just so to ensure that our abort rate reduction makes really a performance gain. So this is our experiment so far, and just to summarize, so we talked about three main ideas of generic VC. First one is reintroducing nested transaction so that we can support Git-style flexible branching. And we talked about having a configurable commit validation phase with two user-defined functions called detect conflicts and reconcile conflicts. With the detect conflicts, we can basically, not we, but whoever the database developer or the application developer is, they can define what a conflict means for their own specific use case. And if they can do that, maybe they can also reconcile some changes and help reduce abort rates. Yeah, that's pretty much it from my side. If you have any questions, I would be happy to answer them.
Yeah, questions?
Oh, thank you.
Maybe first, thanks. Thanks. Any questions?
Yeah.
What happens in the phase when you're detecting conflicts and you detect deadlock? Is there a part that takes care of that?
I detect deadlock.
Yeah.
So, I mean, this is actually, we don't really have many locks in this system, since we don't even do write locks, because, I mean, normally in a traditional system, you at least have write locks, even though this is optimistic concurrency control. But here we don't even do that. So I'm not sure where we really get a write lock here, or sorry, a deadlock here. Yeah, I mean, if you have a specific example in mind, we could also. Yeah?
So at the beginning of the talk, I thought you wanted to bring Git and MVCC to a common ground such that both sides can profit from this. And in the end, I get the feeling that only MVCC is getting benefits from it, from taking Git features to it. Is Git also gaining something from this research?
Yeah, that's a really good question. As database researchers, we mainly focused on if there were anything to gain for database world. Let me think. For Git, I mean, the only advantage would be that you don't have to maintain two different systems. I mean, if you had only a single system that could work both for, like, you know, if you think about it like this, you have any kind of storage, it could be a file system, it could be a database system, it doesn't matter. You have one system that implements concurrency control for all of them. So this is like more on this logical kind of philosophical plane talking about this. And I think if we only had this one system that can be helpful for any kind of data storage format you had, Git could also gain from this, because then the maintenance would be just like having to keep this one system up to date rather than trying to focus on all the different, like maintaining all different formats, data storage formats. So that's
maybe if I add to that, I mean, one could be the conflict detection. I mean, you explained in Git there's this hard-coded semantic algorithm. Right. If that were configurable, you could also do these kind of things.
Yeah, also right, because like in Git you can have like you can version control a software repository, but you can also version control a blog or something. Like there are also very different use cases to use Git. So yeah, exactly. You could
it has sure maybe a database people. It's more like learning for the database world. So I think it's an excellent question. So I think we, of course, then we focused a bit more on fixing these things for database in a generic system. But I think maybe we could think more about, okay, now how to fix Git, right?
Yeah, right.
Interesting. Other questions? Yeah, so what's the point of having file systems, Git on top, and database systems separately? I'm more and more wondering what the heck, why are we doing this, right? I mean, for legacy, sure. But is there any technical reason for, as you're saying, we use this common system that supports all of these features, versioning, file system stuff, transactions across all kinds of blobs, file formats, data models and whatnot. Currently we have this zoo of key value stores, relational system, Git, file system, blah, 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 which leads to many technical problems as well. Is there any other, does someone see any technical issue there other than legacy, and that's how it is, and things evolved like that, but I don't know.
Maybe not a technical issue, but also systems could be better if they are more optimized for specific use cases. So maybe it's sensible to have different Git and file systems, because they're just so differently used that it makes sense to optimize them differently.
Yeah, that's excellent. That's actually a common argument made. So there were attempts, for instance, by Microsoft 15 years ago, I think it was called WinFS or something like that, to implement the file system interface by using a relational database system. And I think it's not done anymore. There are a couple of other approaches, and that's a common argument. But from the point of view of cost-based query optimization, it's not an argument, because if you do it the right way, you could make these systems as efficient as the dedicated special purpose systems. It's more difficult, I fully agree, yeah. But it's doable in principle, you know. Sure, it's an efficiency argument that's often played, yeah, but the other is usability and features you would gain, right? So, I mean, usability, I'm thinking aloud a little bit. Because it's along the similar lines. So these recordings of the lectures, of course, I have to do post-processing and an editing software. I'm using Premiere Pro from Adobe so far. I'm not going to say anything, just look at the expression on my face. I'm currently switching to DaVinci Resolve, which is so cool. But what I stumbled upon is a similar issue here is, where are my files in DaVinci Resolve? It's kind of a storage object, hidden directory thing. And now if I have the files for like one lecture, like for today's lecture, I was really confused. Where the heck are my files? How do I put them separately? And I could see something similar happening if you had a database rather than a file system. In a file system, you see directly, okay, these are the files I've been working on, that's the stuff, and I sent it to an email or something like that. But if it's this magic database, it's not so clear what is the data, what did you change, what are your files you currently worked on. So it requires some thinking into this and thinking into this new world. Maybe that might be in the way at some point, right? I don't know. I mean, you could always have an export functionality. Ask the system, okay, export or show me what I just changed, what I changed today, and can I wrap that and send it by email or something like that. Yeah. But what I'm trying to say is the notion or the idea of having files is maybe so deeply woven into our brains that it's hard to get rid of that. It's just an idea. Anyway.
I mean, one feedback we received from reviewers were like in the lines of, why don't you think about concurrency control as a service?
Yeah.
So like you implement it as a different system, and then you can just put it on top of any type of like key value store, relational or file system.
Right.
Yeah, that was.
Yeah, but with the MVCC store we developed in the lecture, it's not bound to a specific data model. You can do that anyway.
Right, right.
If you do something like that on top, then you have all of that in one system. Naja, whatever. Okay. More research to do. Okay. Yeah, thanks for the great lecture.
Yeah, thank you.